Welcome back. Today we're doing a big picture review of a topic that's, well, everywhere. From baking a cake to how life itself works. We're talking about chemical kinetics. This is your chapter summary. We're going to hit the highlights, the key terms, and the must-know equations all in one spot. All right, let's get into it.
So first things first, take a look at this lizard. You might think he's just catching some rays, working on his tan, but no, this is way more serious. This lizard's survival literally depends on the sun. Why? Well, the heat speeds up the chemical reactions happening inside its muscles. A warmer lizard is a faster lizard, and that's absolutely crucial for grabbing lunch and not becoming lunch. And that, right there, is the heart of chemical kinetics, the study of how fast chemical reactions happen.
So here's our game plan for this review. We'll kick things off with why reaction speed is such a big deal. Then we'll get into the essential vocabulary, so you can speak the language. After that, we'll look at the key equations that let us do the math. And finally, we'll wrap it all up with a bird's-eye view of the entire chapter. All right, let's jump into our first topic. Why does speed matter so much? We just saw with our lizard friend that it can literally be a matter of life and death. Chemical kinetics is the field of chemistry that digs into this. It's all about understanding reaction rates and the step-by-step processes happening at the molecular level that make things go. In chemistry, we're almost always trying to answer three huge questions. The first one, will this reaction even happen? And that's a job for thermodynamics. But for this chapter, we are laser-focused on the other two. How fast is it going to go? And what's actually happening down there with the molecules? Those are the core questions of kinetics. Okay, so to really get a grip on the how and how fast, we need to learn the lingo. Think of these next few slides as your personal dictionary for the chapter. These are the words that build the foundation for everything else we're going to talk about.
All right, here's our first batch of key terms. Now, I'm not going to read all of these to you. This is for you. This is your chance to hit pause and really review them. But a couple to keep an eye on. Activation energy. That's basically the minimum energy required for a reaction to even get started. And collision theory. That's the model that explains why that energy is so darn important. These are the building blocks, folks.
And here's our next set. Again, go ahead and pause if you need to let these sink in. Definitely pay attention to integrated rate law and rate constant. Trust me, these two are going to be the stars of the show when we get to the math in just a bit. They're the tools that give us real power to predict what's going to happen. And here's our last list of words. The two I want you to notice here are rate determining step and reaction mechanism. These are so important because they help tell the story of a reaction. It's not just one thing happening, it's a whole sequence of events. Okay, our vocabulary is locked in. Let's see how these words come to life in the language of math.
So, we've got the language down. Now let's check out the mathematical toolkit we use to actually describe and predict how fast these reactions go.
This is where it all starts. Now, I know it might look a little intense, but the idea here is actually really simple. Think of it like a conversion factor. It lets us connect the speed at which a reactant, A, is disappearing to the speed at which a product, B, is appearing. We just use those little A and B coefficients from the balanced equation. It's all about looking at the same rate from different points of view.
Okay, this is where things get really cool, because this table gives us a kind of chemical crystal ball. These are the integrated rate laws for zero, first, and second-order reactions. They let us calculate the exact concentration of a reactant at any point in time. And right alongside them, you have the half-life equations, which tell you exactly how long it takes for half of your stuff to get used up. Super useful.
And finally, we have the famous Arrhenius equation, shown here in its three most common outfits. This equation is brilliant. It perfectly connects the rate constant K, the activation energy EA, and the temperature T. This is the math that explains how temperature changes the speed of a reaction, just like with our sunbathing lizard.
All right, we've got the vocabulary, we've got the equations. Now let's walk through the chapter summary and see how all these pieces click together section by section.
So, Section 1 is all about laying the foundation. It's just defining what a reaction rate is. We measure it by watching how fast a reactant disappears or how fast a product appears over time. And that very first equation we looked at for relative rates, that's the key tool here. Section 2 covers the four main dials we can turn to control a reaction's speed. If you increase the surface area, the concentration, or the temperature, you're almost always going to speed things up. And then you have catalysts. They're like little chemical shortcuts, creating an easier, lower energy path for the reaction to take.
Next up, rate laws. Now this is a super important point. You cannot, I repeat, cannot figure out a rate law just by looking at the balanced chemical equation. You have to figure it out through experiments. The rate law tells you exactly how much the concentration of each reactant impacts the overall speed, using what we call reaction orders.
So building on those rate laws, Section 4 brings us to the integrated rate laws, that table of equations we saw a minute ago. These are what let us go from knowing the rate right now to predicting the concentration at any point in the future. And this is also where that whole idea of half-life becomes incredibly handy.
So why does all this work? Why does temperature matter? Section 5 explains it all with collision theory. It says that for a reaction to actually happen, molecules have to smash into each other with two things: enough energy, that's the activation energy, and the correct physical alignment. The Arrhenius equation? That's just the mathematical version of this exact theory.
You know, most reactions don't just happen in one big explosive step. They actually happen through a series of smaller, individual steps we call a reaction mechanism. The overall speed of the whole thing is totally controlled by the slowest step in that sequence. We call that the rate-determining step. Think of it like the biggest traffic jam on a highway. It controls the flow of everything.
And finally, Section 7 brings us right back to catalysts. A catalyst works its magic by actually changing the reaction mechanism. It introduces a brand new pathway that has a lower activation energy, so the reaction gets faster, but you still end up at the same destination. It's a shortcut, not a detour. And that's it. That's the grand tour of chemical kinetics. We've covered the language, the math, and the big ideas that explain why some reactions are over in a flash and others take centuries. So the last thing I want to leave you with is a question. Now that you know what pulls the levers on reaction speed, what everyday process, from cooking dinner to watching something rust, are you going to see in a whole new light?